sort of the field, the flux linkages, or we can use. I have used confuse you too much so early. I have used C as for flux linkages. CR. You know that the derivative of flux linkages, that is the induced, like the induced voltages. We call it V over U. So it means that the minus the derivative will lead the flux linkages 90 degrees, right? Which is a minus, so we will have the voltage here, and we will have the field or internal voltage as 90 degrees on that one, and we will have an expression of the armature reaction that is 90 degrees on this, so that will close this in a way. So it's just that I need the so why did I talk about that? Because to make a very short story about the relationship between the voltage vector and the magnetic flux vector and the physical position of the rotor. Because the physical position of the rotor defines that internal voltage. Machines, it's not, these fluxes are not really exactly symmetrical due to the saliency of the rotor. So you have one set of vector here, which is JXD times ID, and one vector here that is JXQ times IQ. And that defines the D and Q axis, right? Q axis, D axis. And this is the sort of internal voltage. Now, the way of, when you're working on this, the way of finding then the rotor angle, this is then the rotor angle. This is the power factor, which I call phi. The way of doing, of finding then initially, if you know the current, you can compute xq times I, and you end up here, and you can draw the line, and you have the q-axis current. Then, of course, you can find the d-axis. Currents. IQ and ID. And then this is the steady state phasor diagram. This is nice, but and it's sort of course, it's valid for in steady state. But the thing is that this these fluxes, and that's why I started to talk about fluxes and flux linkages. They don't change instantaneously. So to take into account that the rotor flux does not change instantaneously. We have usually we define something we call the transient internal voltage. EQ dash, for example, which is somehow related to the flux linkage of the rotor. That's why I started this to understand there is these variables that we talk about, these vectors. They have sort of a physical explanation, but it's not always obvious what it is. But in my head, when I talk about the transient internal voltage, it has to do with the flux linkage of the rotor. And the EF is proportional. EF for EQ. EF is EQ. That is more or less proportional to the applied field voltage, the magnitude of it. And that for that we define also the transient reactance. XD dash. And if you compute XD dash times ID, you come here and then you have XQ times IQ. Then we have defined the EQ dash. We can go one step further if we want. That's the phasor diagram that my students have to learn to draw. We can go one step further and also take into account the effect of damper windings in the generator. We then define for the damper, we define EQ double dash and ED double dash X E double dash X. And then the phasor diagram, if we want to, did I get any more colors? Maybe blue would be nice. Blue for the damper windings. You have, for example, something like that. XD double dash times ID and XQ double dash times IQ. And then you have the E, the subtransient internal voltage. This is sort of basically my understanding of the electrical machine and the synchronous machine, and what I need to know to develop the dynamic models. And one thing we can derive from this one is the expressions for electric power. And then we have two different expressions, depending on if we express it as a function of the steady state parameters or the transient parameters. And it is not anything mysterious about this. For a given operating point, it will give the same power, but the equation is different because we express it as a function of different parameters. I mean, we can express voltage as a function of power as a function of the steady state variables EF, Vs, IQ, XQ, and XD. Then you obtain this formula, and you see if it's a round rotor machine, XQ and XD are equal, so this will be 0. So then you're back to the simple expression, and you, in the same way, you can express power as a function of Vs and EQ dash, and the same angle, and you get this expression. That involves the transient reactance as well. You can see this is just about I mean, both these equations are derived and that could be an exercise. I mean, the power is it is the power supplied to the and the swing equation is just Newton's second law on the side, taking into account that the generating units can be looked at as a oscillating system with well, basically you could include different stages in the turbines as high pressure, low pressure turbines, and stiffness on the valves, and you could consider the different generators in a power system as masses that are coupled with springs and dampers. But anyway, we'll start simple. But the way of looking at it is that this is rotating masses, and you define the angle of the rotation, the speed of rotation. So this is then fairly simple from the start. You have a mechanical torque from the turbine, and there is an electrical torque in the air gap due to the power that is converted to electricity, right? And then, I mean, it's simply Newton. The difference between the mechanical power and the electrical power will accelerate the rotor, and the proportionality constant is the inertia of the masses. So this is the swing equation that we need to take into account. The problem is only that it appears in many forms, different scales, and so I just break. Yeah, we have some 10 minutes. How I look at it. But this is, of course, the basic, and you might see that there might be some frictional damping or whatever that is proportional to speed. So you might have a damping factor, but that's not so important now. Is how you use this equation. And the other thing to say is that basically the speed is the derivative of the angle. So the t of the rotor angle is speed. This is it. And then you can, of course, integrate everything and turn it into a second-order differential equation like this. But the importance, I think, is how you use it. If you understand the basics here about the balance, mechanical power in, electrical power slowing the rotation down, and the balance and the the basic differential equation, understanding, I choose some basis. Take away. What I do is that I have a power base that I have to choose. I have a speed base that is usually and from that I can derive a base for torque and damping and other things. But this is the most important for the mechanical part. And what I then apply is the inertia constant. That is what I'm using, which is that is sort of the thinking behind that is that this is the kinetic energy of the rotating mass divided by power, meaning that this comes in seconds. As it's measured in seconds, and therefore it's more easy to relate to. So that means if we do the transformation to per unit, we end up in my lectures with two equations. That you have 2 times h times the omega dt is, now I called it T mechanical minus T electrical, and then I would retain delta in radians. So d dt of delta is then 2p times omega n times omega, because this is omega in radians, right? This is the base. It's the base times the per unit. Now this is in per unit. This is, maybe I should, not to confuse, I should use another term for this. When it's in radians per second, it would be a uppercase omega, for example. And then omega is in per unit. It's very to confuse on these things. That's why I talk about it. And then the next thing I would do, I would express I would express in power instead. Power is torque times speed, and if I multiply that, I would get 2h omega times the derivative of omega. Now I use that as a dot. That would be PM minus P electric. And then I could say that, okay, this is usually around 1 per unit. So I just forget about it. So in most of the continuation, I would consider that as the swing equation. So that is what we end up with. That is our second order model. And then we can, well, we can apply the S Laplace transform, depicted as a block diagram. This is exactly the same as my two equations. And you can start analyzing if you want, but it's not that interesting. So what we need to do now, we can do that before the break, is that we can have a close look at what we have. What is this? Of course, is our characteristic now expressed as a function of the internal voltage and the power angle. And if you, and this of course is a nonlinear relationship, but if you try to linearize it, you can linearize it with respect to delta. And then you find what we call the synchronization constant, right? It's the sensitivity of power with respect to a change in rotor angle. You could also make a sensitivity with respect to your internal voltage, but we come back to that later. That would be like this. We could also include the damper windings and try to compute the sensitivity of the power with respect to speed due to the damper windings. We could linearize that. We also have a linearization constant for that we include. We can include that in the D. So the effect of the damper windings could come in here, because it gives a damping effect, mainly. And if we use that, we know, then we have something that connects the delta with the power through the synchronization constant. We can come back to the damper windings, but if we connect, we have this one. And then we have something to start with for the analysis. We have a second order dynamic model of a generator connected to a strong grid. And I think then it's a good time to take a break, because then we can illustrate that a little bit after the break. So, yeah, any questions? I mean, was this too simple, too basic? Or is it okay as a repetition? Yeah. Hmm?
If you can have some hour left for the interaction between the participant and you.
Yeah.
Maybe on this.
Yeah, I mean, I would.
Free actually. Then we can discuss what could be the scope of the research, and then whatever the questions you have related.
And also, I would like to maybe when we have a tutorial tomorrow,